Hello, beautiful people that is watching this. I have no idea when you will be watching, but it could be at any point in the future. So today, this is a daily effort. I just want to have a log of multiple things, and I enjoy programming and just for the sake of programming. So let's get a little bit of a. This is going to be a series of little ideas and then how to solve them, right? So today I want to do a scale quantizer, right? Yes, and of course it's important to mention that I am going to program something for the Kontakt platform. I mean, it's in the title, right? So excuse me for a second. I need to check this. Okay, so I don't want Cubase. Nope, I said I don't want Cubase. I want this guy. Okay, yeah, it's cool for you to see it because, you know, I just like some mouse shortcuts. They are very helpful. So I press here or press here. In this case, we're gonna start something from the absolute scratch. So let's go. So let's do this. Let's get our folder going. Well, first of all, let's talk about this problem. So to me, solving problems in programming is basically like a math problem or a puzzle. First you have a question or something you want to do, and then you think, you know, how to get there, basically, you know, just step by step. So what happens, let's just talk through this. What happens here? We have an input from MIDI, right? And when we have an input, the on note, the note callback will be called, will run, and then we have notes coming in, right? Whatever. I mean, let's put numbers, for instance. And we want these notes to conform to a certain scale. Well, how do we do that? So, of course, there's, you know, people that are like super snappy about solving these problems. This is not pre-solved. I'm just gonna go around this as we speak, and I think for a lot of people this can be useful because of the thought process. So, okay, let's say a scale basically is what? It's a collection of notes. But more than a collection of notes, it has, let's say, it has a root. What are the characteristics? That's great. Characteristics of a scale. So it has a root, right? So it's either C, C sharp, E flat, etc. So I'll talk about how to identify the root of a scale, no matter in what octave it is, right? And then after a root, it has a structure. The structure is basically the distance between the intervals. So if we get the major scale, we're gonna have these numbers. Actually, let's do a zero based, right? So C, then D, then E, then F, then G, then A, then B, and that's it, right? So let's write it up here so it's a little easier to see, to visualize, let's say. Right, so we know that our scale is has this structure, right? So no matter the number that you pick, let's say you pick 64. So how do we convert 64 to this? Well, we use this operation mathematics called modulo. So the modulo is when you divide a number by another number and you take the remainder of it. So if we say, let's use this, let's just write. So 64 modulo 12, well, 60 divided by 12 is 5, and the remainder will be 4, right? The remainder of this division. So in this case, 64 is the note E. Okay, so this part is easy, no problem. Now, the problem or the challenge is when we get 65, for instance, then what do we do? Because 65, oh, okay, 65 is going to be F. Let's do 66. So 66, let's say by default, we will always do modulo. So it's going to be 6, which is F sharp. Now, the question is, should we quantize up or down? How about this? Well, it's kind of arbitrary, right? It's just subjective. Let's say if we are in C sharp and we go always down, goes to C, then D sharp goes to D. We're not going to have E sharp, we're going to have F sharp, let's say go to F, then G sharp goes to G, A sharp goes to A, and then we're not going to have anything here. I think for the sake of I'm thinking of a few things. Let's say if you have a scale with sharps, and well, C is not a great example because it doesn't have any sharp, but let's say D major. So it's D, E, F sharp, G, A, B, C sharp, right? So if we get any notes outside of this, let's say F, you know, my traditional harmony thinking wants me to do this, right? So F would go to E because it's closer to E. Well, it's not closer to E, but if you think in tonal terms, F being the minor ninth of E belongs to, for instance, let's say if you are in C, F would be the seventh of G, so G is the dominant, so it's the seventh of the dominant, and the seventh usually goes down to the third, right? So the G major seventh chord going to the C major chord. It could be interpreted in a different way, but okay, let's do this. Let's do easy. Let's make it so it always goes down. Okay, so we are talking about transformations, right? So if we have the number, let's say we have the number 1, let's say you get 61, right? 61 will be C sharp. Let's go back to C major. So we apply the modulo, and we're gonna get 1 because 60 divided by 12 is, wait, am I doing this right? 61 divided by 12, yes, it would be 5, and then the remainder is 1. Okay, then if our choice is to always go down, then, well, the first thing we have to do is see, okay, where is 1 in this sequence, right? What is it the closest to? So let's see. We would have to do an algorithm that would basically do what? It would take this sequence, check the first element and say, is our number is our number equal to what is in the position 1? Let's say we have our C major scale. It's going to be a an array, so it's a list of array, list, set. It's a bag of elements, right? And in this case, let's do it this way. It's this is pseudocode, right? This is not any kind of code. I mean, it's kind of code. It's pseudocode. So we have 7 positions, right? So the thing is it equal to the first? Is equal, and then I think we should also ask, is it bigger than the first? And then this would be false, right? And this would be true. Now, then we can do, is it, let's do this, is n equal to our second element? No, it's not. It's false. False. Then is n bigger than 1? False. Oh, okay. So we have, let's say we can do 4 checks. I'm sure there's a better algorithm for this, but let's go with this. We do 4 checks with 2 positions. I mean, we would have, let's say, with 1 position, we know that it's the position and the position plus 1, right? So we do 4 checks, and we will know that n is between these 2. So then, in the end, if this is false, this is true, this is false, and this is false, we know that n will be between the element 0, the very first element, the 0th element, and the first element, right? 0th element is bizarre to say, so let's say first and second element, but on an array that is it's 0-based index, right? So then we know that it's in the middle. So if it's in the middle, all we have to do to quantize, let's say the quantized node would be the node of that of the incoming node minus 1. So if that node was we set 61, right, which is C#, let's just put it here, C#, then in this process C# becomes C. Does it make sense? Okay, let's recap. So we are doing a scale quantizer. We talked that every scale has a root, every scale has a structure. This structure is based on the intervals between the nodes, right? And then we are going to store these nodes on a list to be for convenience, because every time we need to check something about the structure of our scale, let's say we need to compare something to 1 element or 2 elements or more, we just reference that, what we call a data structure, and then we visited a very simple algorithm that will place this number. Is it, given a certain position? We started with the first position. We will compare between the first and the second position, and if these conditions have these results, this means that we can go ahead and do this to our node, do the transformation to our node. Okay, Now let's formalize this a little more, because there's more steps. Because what if the note is not equal to the second element? Okay, so it's false, but this one is true. Well, here's one thing I love doing, and I always recommend people to do. So I'm using Figma here. It's definitely not a program to do what I'm about to do, but it's capable enough. So let's do this. Let's put a little text inside. Let's see. So we're gonna have an input node. So input node, right? Let me do it this way. I think it's, like I said, Figma is not made for this, but it's pretty capable to do what I want to do, which is a fluxogram, or a flux diagram, or no, what is it? I'm mixing mixing languages here. It's a flowchart, let's say. All right, so we're gonna have an input node. We immediately are going to I'm gonna just draw this. We don't need to make this very pretty. We immediately are going to do an operation. So we're gonna have our let's say I'm gonna call SN. So standardized node, it's the node mod 12. So if node 61, mod 12 is going to be 1. If it's 66, it's going to be 6, etc. Right? And 61, you know, these are the MIDI MIDI nodes. The number of the MIDI nodes has, you know, they come in from a MIDI controller or from your DAW. So let's say from 0 to 127, right? So that's the range. All right. So from here, we would there's a few steps and I'm gonna do this in a not very linear fashion, but the steps are we have to fall into these 4 checks, right? So how do we do that? Well, the way that we're going to do that is because I know that I'm gonna add something later, I'm gonna do this. Let's do. Actually, let's do it this way. It's this isn't. You see, bear with me that this is worth it. Let's do this. Then let's do 45 degrees, and this let's do 45. Oh. Or let's say 0. Okay, very pretty. So usually in flowchart land, we call these diamond shapes the conditions, right? So because here you know that something happened, this is an assignment, and this is going to be a condition. So we go to our note array. Let's call it in. And let's say so is the very first element, so we do like this, is n equal to the very first element? That's a very important and valid question. Let me put this here. So well, we have 2 possibilities. So 1, it's not, and 1, yes. So let's do that. So we have a no, and we have a yes. Then what happens? So if it's a false, then we keep going. So actually, let me trade these 2 guys, because the yes is another case. So if it's a false, then we want to check something else. Right. And then the question is it bigger than the first element? And we want it to be true. So we're going to pay attention in case it's true. But in case it's not, we have to have a path for that. Okay, let's keep going. So here we have one more question. So let's do it. So is it equal to the next element? And then we have these two possibilities, and we want it to not be, right? But we also have to treat the possibility that it is. And then we have finally the last one, which is it bigger than? And if it's false, then we will then we finally reach what we needed, right? So this is a no, but we also have the yes. Now let's see. So this, yeah, things can get pretty big pretty fast. So if it's a no, then what we are going to do, there will be other commands in here, but basically what we are going to do is, so the n is our, oh, and I'm sorry, because this is supposed to be sn, because the scale inside of the array will be in this form of this very first numbers, not like 60, 62, 64, 65, etc. But then what we want here is that n will be n minus 1, right? So if the sequence gets us here, this path. Now there's one very interesting thing. But the thing is, what if, yeah, I mean, it's not equal. I mean, what if it is equal to the first to the first element? Well, then basically we have to find a way to exit, because it's fine. If it's we don't need to quantize that. Okay, so. And if it's not bigger, then let's see. So if it's not bigger than the first element, there's only there's two possibilities. It has to be. I mean, if it is bigger, I'm sorry. It's a little late. Excuses. All right. If it is not bigger, it means that, well, it means that it's the same, right? So I don't think we would even get to this branch. So let's do this for now, right? So I don't think there is but it's important to maintain this, because let's see. Let me think for a second here, and you think there, I'll think here. Okay, so I thought for a second, and it seems like this condition, it's not needed, because let's say if our number is 1 and it's not equal to the first element, then when we get here, yes, it is going to be bigger. So we can assume that if it's not the first element, it has to be bigger, right? And you could say, well, but what if the number that we are checking is like number 5, and it or 6, for instance, and then the element that you're checking is the element 7. Well, the thing is that we wouldn't be checking the element 7, and you will see now why. So for now, I'm going to just remove this. Just going to leave this here for a second, right? And I'm going to bring these guys here. And why is that? Because we will know that if we don't get to this path, but we have to keep going. So let's say our number is 6. Well, if we're checking against 0, it's not 0. Is it equal to 1? No, it's not. Is it bigger? Yes, and actually, yeah, it's bigger. So in this case, we would go to this branch, which is we have to restart this, but with different indices. So basically, we're talking about a loop, right? So we're gonna have to repeat this whole part. So let's see. Let's go to this question. So let's say we are still working with number 1. So Sn, the standardized number, or the modulo of the number, it could be Mn, but Sn is easier. So this is false. Okay, so we get here. Then is 1 equal to 2? No, it's not. But what if it is? Well, if 1 is equal to 2, is the same thing. We exit because we don't need to quantize, right? So very simple. Then next one is 1 bigger than 2? Well, in this case, it's not, but maybe in the loop it could be. So okay, so that's a no, and then we got here. So let's test. Let's say, okay, but what if it was a number that was bigger? Let's get 6. So is 6 equal to 0? No. Is 6 equal to 2? No. So is 6 bigger than 2? Yes. Oh, so then we have to loop. Actually, I'm not going to exit. So let's do this. Then we have to loop. And then how do we loop? Well, in this case, I'm going to do... let's do this. Actually, there's a few things that we have to do first. We have to... Well, first of all, we're gonna have to use a counter, right? Let's call it C. So C is the counter, and here is the counter plus 1, right? So then what we're gonna do is we're going to do C. We're gonna increase, increment C, and then we're gonna come from here to back to here. I'm sure there's some more things that we have to check, but because, for instance, let's say if the number is 10 and we are checking, let's say our counter is in position 0, 1, 2, 3, 4, 5. So C equals 5, let's say. So is 10 equal to 9? No. Okay. Is 10 equal to 11? No. Is 10 bigger than 11? No. So then quantize. Now, what if it was 11? Is 10 equal to 9? No. Is 10 equal to 11? Yes. Exit. Okay, so I was just checking if at some point we would have a part of the loop that C would, just get to an index that doesn't exist in our array. But for now, it seems like it's pretty solid. I could be missing something, but I think the best way to do this is to check your algorithm is test a couple of numbers, maybe 3 numbers, edge cases, right? You can test 0, you can test 1, so they're close here. You test one number right in the middle, maybe a 6, which we did, and then we test a 10 and an 11. And I mean, it doesn't make any sense to test 12 or higher numbers because we are standardizing the number right here. So, well, of course, there's minor details like the counter has to be initialized when we start the loop for the first time. So we could do something like this. Let's say we call c equals 0, for instance. So there you go. This is how you program. This is how you think about solving problems. This is a simple one, very simple. But this is the basis, right? So for this to not be extremely long, I'm going to cut it here and come back on the next video. So see you then.